All right, hey everyone, welcome to the stream. Welcome to the stream. Is everything running well, smooth? Yeah, let me know. Hello, hello. So today we are gonna take a look at Rust. There's been a lot of hype about Rust lately, so even I was thinking that I should start. I should take a look at it. Yeah, we're gonna go through a brief intro about what is Rust about, what are the news, why is there the hype, and then I'm gonna go through this tour of Rust where I'm gonna go to get a review, learn Rust, and yeah, my main focus right now is TypeScript. So I expect myself to compare everything to TypeScript. So I hope it's gonna end well. Um, and yeah, so um, I think we can slowly get started. So if you take a look here, I found some articles. Here's something on Stack Overflow. What's Rust and why it's so popular? So let's take a look at it. Um, what do we have here? Uh, so coming from dynamically typed language, that's me. That's me. I'm coming from Node.js TypeScript world. Uh, the arguments between programmers who prefer dynamic versus static type systems are likely to endure for decades more. But it's hard to argue about the benefits of static types. Yeah, definitely. I mean, when I was starting out, I started with PHP, and like I don't know, 10 years ago, maybe even more. And I really like that I don't have to care about types because I didn't really understand types, and the reason for it, I just wanted to get the job done. But then slowly I got to a point where I love to use types. I squeeze everything I can from types. I type everything, and this way I make sure that the software is gonna work. Uh, so really glad there is a pushback against it, against the dynamic languages, and people are more and more moving to types, as we see with TypeScript. So yeah, mainly statically typed languages have large asterisk next to them. They follow the concept of null. This means any value may be what it is or nothing, effectively creating a second possible type for every type. Yeah, that's this thing called undefined we know from JavaScript. And yeah, it can break a lot of stuff. Uh yeah, Rust encodes this possibility using an optional type. Yeah, that's fair enough, right? Something we know even from TypeScript, I would say. This prevents occurrences of a dreaded type error, cannot read property foo of null runtime error. Yeah, that's classic in JavaScript, right? Here's an example of function to greet someone whether or not we know their name. If we had forgotten the none case in the match of tried to use name as if it was an always present string value, the compiler would complain. So greet user, we give the name, which is optional. We match name, and if the name is some, which probably means like anything except none, we will print it out, and if it matches none, then we got this. I really like the syntax because it's very visible, clearly visible what you are matching, and you see all the options. So yeah, that's static typing. What do we have here? Some statically typed languages place a large burden on programmer, requiring them to repeat the type of variable multiple times, which hinders readability and refactoring. So what do we have here? What is Rust doing? Rust learns from both of these styles and requires top-level items like function arguments and constants to have explicit types while allowing type inference inside of function bodies. In this example, a Rust compiler can infer the type of twice, 2, and 1 because the val parameter and the return type are declared as 32-bit signed integers. Yeah, so we can see here we don't really need to define the type. Yeah, fair enough. Coming from garbage collected languages. Oh yeah. Rust gives you the choice of storing the data on the stack or on the heap, and determines at the compile time when memory is no longer needed and can be cleaned up. This allows efficient usage of memory as well as more performant memory access. Yeah, so classic languages, you have the garbage collector, so you are defining variables, and then the runtime on the background is searching for stuff that you are no longer using, which let's say it's a certain overhead, and it can slow down the app, or make everything more complicated and complex. And here Rust is automatically able to based on your code, determine when is the right time to clean up the value from the memory. So yeah, I mean, that's pretty cool. Definitely makes sense. And what do we have here? Yeah, to many people, Rust is largely viewed as an alternative to other systems programming languages like C or C++. Yeah, that's what many people are saying. Or Go, some people say. The biggest benefit of Rust can provide compared to these languages is the borrow checker. This is the part of the compiler responsible for ensuring that the references do not outlive the data they refer to, and it helps eliminate entire class of bugs caused by memory and safety. Yeah, Rust is very much focused on memory safety, and yeah, that's very helpful. I mean, that's why everybody's so afraid of C, C++. People don't want to work with the memory so tightly, so they prevent themselves and colleagues and everybody in the team, from introducing some memory leaks. And yeah, it's not all roses. Strong type system and emphasis on memory safety to get errors when compiling your code. Okay, yeah, I mean, I like that actually. I like very much when I get an error during compilation, and I write my code in a way that if something changes on the other side of the code base, the app is not compilable. There are many tricks you can do in TypeScript, like if you have some configuration and it correlates with some other part of your code, you are able to write like switch cases and other stuff like that will fail the compilation to make sure that the app is properly configured and prepared for the deployment. So that's good. And in this example, we create a mutable string containing a name, then take a reference the first 3 bytes of the name. While that reference is outstanding, we attempt to mutate the string by clearing it. There is now no guarantee that the reference points to valid data, and dereferencing it could lead to undefined behavior, so the compiler stops us. Well, cannot borrow name as mutable because it's also borrowed as immutable. Yeah, I mean, it's pretty fair enough. Well, I mean, this all makes it super hard for junior developers, but super well maintainable for senior developers. So there is this clash between people getting in versus like growing a big and sustainable business on it. TypeScript and JavaScript ecosystem is very helpful, but of course I can see very often that there is some feature in TypeScript which could be much better, but it's limited by the fact that it's still JavaScript. Like for example, errors. Error handling in JavaScript ecosystem is so broken. You never know what error it's going to throw, and that's really bad. I mean, in other languages, like in Java, you have this throws keyword, which tells you what the function may throw as an error. So this way you are able to prepare a code base that handles all possible error scenarios. But in JavaScript, you never know what kind of error is it going to throw, and so getting ready to handling errors in JavaScript, most people only handle happy path. All right, so yeah, that's one intro article. Let's move on. Yeah, we have some comparison with TypeScript, so let's get it quick. So yeah, we are creating our constant x, then y, and in Rust, yeah, I mean, it's the we are not just saying number. It's like 32-bit integer, if I'm not mistaken. And then we need to use this, I guess, pointer syntax for strings and stuff like that. That's fair enough. Yeah, instead of interfaces, we create enum, not interfaces. Oh yeah, enums. Yeah, I mean TypeScript. Yeah, that's the problem with TypeScript. Like it added support for enums, but then you can also do stuff like this, like use the string literal types and stuff like that. And then we are at a meeting and we are discussing which we are going to use, and both of them are valid ways, you know. But the fact that you need to decide, oh, that's so bad. So yeah, we have interfaces here, then we use structs instead. That's also in other languages. What do we have here? I see. TypeScript most use functions. In Rust, you are encouraged to define such operation as a method on structs. Okay, that will be interesting. All right, update user, and you get self, and then you mutate the self part. Okay. Yeah. Never mind. Yeah, let's get started with the tour of Rust. I think there will be a lot of work ahead of us. So yeah, let's get cracking. So where do I begin? I do next. All right, chapter 1, the basics. In this first chapter, we're going to be exploring the very basics with functions, variables, and the most primitive types. Ferris, the unofficial mascot of Rust programming language. Nice to meet you. Once you're familiar with Rust, you can call yourself a Rustakeen. I have no idea how to pronounce this. All right, let's get started. The Rust playground. All right, so we have our playground here. I run this, and welcome to playground. All right, yeah, let me zoom it out a bit. I hope you can see it clearly. If not, let me know. All right, next. Variables are declared using the let keyword. Okay, so TypeScript brought mostly const keyword. Here we have let. When assigning a value, Rust will be able to infer the type of your variable 99% of the time. That's great. If it cannot, you may add your type. Okay. Notice how we can assign the same variable name multiple times. This is called variable shadowing, and the type can be changed for subsequent references to that name. Variable names are always in a snake case. Remember that, people, a snake case. No camel case anymore. Okay, that's the first difference. So we are here redefining variable with completely different type. Rust can also declare and initialize later, but this is rarely done. Oh, come on. No. All right, yeah, this is clear. 13.5.0. Yeah, let's go ahead. Rust cares a great deal about what variables are modifiable. Values fall into two types, mutable and immutable. The compiler will allow the variable to be written to and read from. The compiler will only allow the variable to be read from. Mutable values are denoted with a mute keyword. Okay. I mean, yeah, this is fair enough. In TypeScript, basically, you either use const or let. Const for immutable, let for mutable. Here, you have use for everything let, and then you use mute keyword to say that this is mutable. We will have more to say on this concept. All right, I will run it. So we are setting 32 as mutable. We will print it out, and then we set it to 13 and print it out. Okay, fair enough. Rust has variety of familiar types. Booleans for representing true false, unsigned integers, which means positive numbers only, for representing non-negative whole numbers, signed integers for representing whole numbers, pointer-sized integers. It's good to know. Usize, isize for representing indexes and sizes of things in memory. Yeah, this is something we are not familiar with from TypeScript, so that's gonna be a new one. We have floating point. Yeah, that's decimal numbers, characters. Got it. Yeah, tuples. This stuff we don't. Do we have tuples in TypeScript? I don't even know. Yeah, there is this way, I guess, how to define tuples, right? We have arrays. Slice is a collection of similar elements with length known at runtime. Okay, that's interesting. And we have string, which is string slice, text with a length known at runtime. Okay, text might be more complex than you are used to in other languages. Since Rust is a system programming language, it cares about memory issues you might not be able to use to. We will be going. Numeric types can be explicitly specified by appending the type to the end of the number. Okay, got it. So what do we have in the code? So we defined, by default the number is it is 32-bit integer. Here we define 12 as a unsigned 8-bit integer. Okay. Yeah, I mean, this kind of stuff for beginner developer or people who didn't ever go around. Hey, Roop 12. Oh, Darko, I see. What up? Nice to see you. Welcome to the stream. Where was I? Yeah. So here we have Unicode character. Yeah, emojis are also Unicode characters. Tuples, and yeah, this way I guess we represent individual variables that we can print out. Okay, let's carry on. Oh, thank you, Darko. Yeah, I mean, I really like types in TypeScript, and I was wondering that I would take a look at what magic I can do with types in Rust, and how does it all work, and if it really is worth the switch. So yeah, let's see. I'm really curious. All right. So basic type conversion. It will take a while for you to get used to the whole borrowing system, but do not give up. All right. Yeah. Let's see. Luckily, Rust makes numeric type conversions very easy with the AS keyword. AS. All right. Fair enough. That sounds good. Constants allows us to specify a common value that's used throughout our code many times efficiently, instead of copying values like variables. I've started to learn like 3 times, but ultimately I've stuck with it. That's a great news. Yeah, I mean, I will see. I mean, the biggest argument for JavaScript or TypeScript is that, it's the mainstream language, runtime and everything, and hiring new people is apparently easier. So yeah, let's see if the Rust can make it. I mean, I wish so much, and I mean, this has been here for like a decade or more, that people stopped using. Hey Benjamin, welcome. Yeah, this has been here for more than a decade. That there was a push against JavaScript, but it never really happened. So yeah, let's hope this time we can make it. Yeah, let's carry on. We have constants, so allows to specify common value that's used throughout our code many times efficiently, instead of copying values like variables where are used. Constants directly replace the text identifier where they are used with their value at compile time. Yeah, this makes sense. Arrays is a fixed length collection. This is a game changer, or not a game changer. It's like a game changer is a positive thing. This will, let's say, make it more complicated for us coming from TypeScript world. The data type for array is where T is the elements, and N the elements type, and N is the fixed length. Okay, so we define array like this. So we say it's a 32-bit integer and it's of length free. So here we can see it. Individual elements can be retrieved with the operator where x is use size index. Yeah. Arrays have to be of a fixed type and length. Yeah, I mean, makes sense, but you know, I mean, it's much more easier when it's dynamic. But yeah, I mean, I get it. The reason why Rust is, you know, memory safe and everything is because it does these things. So I totally respect that. Yeah. Collections with a dynamic length, often called dynamic or variable arrays, are introduced later in chapter about vectors. Oh, I see. Vectors, as you say, Darko. Yep. All right, so let's run the code and see what it does. Okay, I guess this is this mentioned here? No. So seems like this is like stringifying the array, and this just prints the value. Let's go. Functions. Function has 0 or more parameters. In this example, the add function takes 2 arguments of type signed integer of 32-bit length. If you just want to return an expression, you can drop the return keyword and the semicolon at the end, as we did in the subtract function. I see. Function names are always in snake case. Everything is snake case. They're just to print the raw array. Yeah, I see. We'll print the raw object array, whatever. You will use that a lot in debugging. Yeah, exactly. Function names are, alright, hint, if you define function, the data it accepts are called parameters. If you call that function and pass data to it, then it's called arguments. Oh yeah, this is some computer science stuff. Yeah. Like some proper university style. Yeah, but it's true. Yeah, it's always good to know the difference. So yeah, we have our function add x and y, and it returns, yeah. I mean, it would be so much easier to say just number, but I don't know if, you know, maybe it is too simple. All right, so yeah, if you want to return, we can do it like this, or we can, it's going to be just this, it's simply just going to be the last value or like last expression in the function. Subtract. So if I run the code, here we go. Fair enough. So if I do like this, how do you call add subtract? Oh man, how do you call fn whatever? We can do it like this. I32, and we are gonna do like this, and I will do, yeah, I mean, I don't know how to pronounce this in English, so I just did this quick shortcut. Never mind. Run. All right, we got it. Yeah, let's carry on. Multiple return values. Wow, okay. Multiple values by returning a top tuple of values. Okay, well, that's easy. Tuple elements can be referenced by their index numbers. Rust supports various kinds of destructing that we will see in many forms, allowing us to extract sub-pieces of data structures in ergonomic ways. Oh yeah, this sounds good. So result swap. Oh, this is interesting to see. Like, you know, that I would expect this to be like this, but it's not. I mean, can I do it? Let me see. Run. No way. Okay, I got it. That's for arrays. You're not in array. And yeah, this destructing looks very good. Yeah. So let's go ahead. Returning nothing. If no return type is specified for a function, it returns an empty tuple, also known as unit. Whoa, okay. Empty tuple is represented by Using empty tuple is uncommon, but will come up often enough that it's good to know that's happening. Okay, yeah, this is like good to know thing. So if I run this, got it, yeah. Stringifying stuff again, as you said, Arco. All right, chapter 1 conclusion. Nice job so far. The basics of Rust aren't so bad, right? Yeah, I mean, it's pretty fair enough. We are getting a peek into how Rust compiler thinks. As a system programming language, it cares a lot about the size of values in memory, whether things can be modified or not, and making sure your math is what you want it to be. My favorite part of Rust is the ability to return a result object from functions. Once you get used to it, it's such a great feature. All right, we're coming to that. I hope we'll see soon what result is. So next time we will looking at some old friends, if and for loops. Okay, let's go. Or brackets. This is fair enough. Seems pretty same like all the other languages. This, yeah. Nothing special. Loop. Break. Oh wow, okay. I see. So instead of while, seems like we have this loop keyword. So we have this mutable x variable, we are adding to it, and if it reaches 42, we will break and print out the result. That sounds good. While, oh wait, okay. So we have really just a loop for infinite loop. Okay. I mean, why not? Why not? While lets you easily add. I mean, yeah, I'm a bit confused why they did it, because I mean, yeah, I mean, if you are running like some server or whatever, you know, which is running in loop, can be, but in the end, mostly you will have some condition how to get out of from the loop, which is while, right? Or do while. Yeah, can be. We have for. Okay, I see. So what is this? A Rust for loop is powerful upgrade. It iterates over values from any expression that evaluates into an iterator. What's an iterator? An iterator is an object that you can ask the question, what's the next item you have? All right, until there are no more items. Okay, we will explore this more in further chapters. In the meantime, just know Rust makes it easy to create iterators that generate a sequence of integer numbers. Yeah, I mean, I know a couple of languages that have something like this. Nice feature. With this double dot operator. Creates an iterator that generates numbers from start number up to nothing, including the end number. Creates an integer that generates numbers from start up to and including the end number. Okay, yeah, so this is going to be 0 1 2 3 4 0 1 2 3 4 up to 5. Yeah, makes sense. Match. Oh, this is lovely. I love these match expressions in the languages. It can be done in TypeScript, but it's like you need to construct it yourself somehow, let's say, and it's not as beautiful as these are. So I'm really happy to see this. Miss your switch statement. Rust is an incredibly useful keyword for matching all possible conditions of value and executing a code path if the match is true. Let's see how it works. Yeah, we'll have more complex in future. Match is exhaustive, so all cases must be handled. Yeah, that's great. Match is huge in Rust. You will use it rather often. Yeah, I mean, and I'm excited to use match because, you know, it's such a great feature. You know, it simplifies everything, I would say. Like, you know, it's so much easier to read than bunch of ifs and stuff like that. So yeah, I'm happy to see this. We can bind the match number to a variable. Whoa, what's that? So let me read that. So if we have for x, if x is 0 on 0, we can match against multipliers. Okay, so 1 or 2. Ranges 3 to 9. And what is this? We can bind the match number to a variable. Match number found number between 10 and 100. Well, this I'm a bit confused about. Oh, come on. But yeah, I guess there might be, because I mean you can use X, right? Why would you need this? But yeah, I guess you can do let X equals match Y. I see. This is the default match. Okay, underscore. Makes sense. Okay, so that's match. I happy to see match. Returning values from loop. A loop can break a return to return a value. Let. Oh. Wow. Okay. What? What's this? How it works? Then, depending on the match outcome, you will assign the value to X. I see. Yeah, like you can have return in match, or you go to previous. Like, yes, loop is. You can. Oh yeah. Is loop is its own scope, so you need to return the value from it. Yeah, I mean that's something new. X equals found 13. But Ben, I'm wondering, like, how does it return? Is it like, and if I do like X like 1? No. Mismatch types. Can break to return a value. So if I do like let z equals 0 and break I, oh wait, no. Oh, I see. Okay, so break is like a return statement. Okay, I see. Well, why not? That's something new. Yeah. Returning values from block expressions. If match functions and scope blocks all have unique way of returning values in Rust. If the last statement in an if match function or scope block is an expression without semicolon, Rust will return it as a value from the block. This is a great way to create logic that returns a value that can be put into new variable. I see. Oh, notice that also allows if statements to operate like an ternary expression. So let's see. So Rust's ternary expression. If I see. Okay. Yeah, that sounds good. So we have if x is lower than 42, we will have this value, else this, and we have hamburger match food. Food is here. If it's hot dog, I mean, I would expect the compiler to maybe like notify me about that this cannot really happen, right? But I guess there are some CLIs for that. Never mind. Notice the braces are optional when it's just a single return expression. Jeez. I see. Braces. Oh, okay. Understand. Yeah. So if there is just this one value, you don't need to put it like this. Am I right? Yeah. You can have it like inline. I will declare this goal blocks lets us get the result without polluting function. Oh, I like this. I mean, I was wondering that I would want this to be in TypeScript many times. Like create my own little scope, deal with some stuff, and then just return it and carry on. So really glad to see this. And then idiomatic way to return value in Rust. Yeah, like it's the last value without a semicolon, so it's gonna be returned. That sounds good. Chapter 2. Hopefully I've shown a glimpse of Rust power even in the most basic language features. We'll be talking about for and match even more in depth. Let's do it. Basic data structure types. Let's go. A struct is a collection of fields. Yeah, it's like an interface or type in TypeScript. String is a struct. Oh, is it? Okay. Warning, struct C creatures never constructed. Yeah, that's what I was talking about before. Yeah, there's the warning. Playground generated by one warning. Alright, let's go. It's basically an object. Is it, though? I thought it's just a type definition. It is type definition, right? Then we create object from it. String from hello world. Using static method to create an instance of string. S. Okay, got it. Static methods. Yes, but you can implement methods to it. Yeah, that's what I was. That's what I noticed here. Not. Yeah, like you can implement methods to it. So yeah, I guess we will get to that. Static methods. Methods that belong to a type itself are called. Okay, instant methods. Yeah, this is fair enough. This makes sense. I believe it's similar in other languages. Yeah, so hello world, 12 characters long. Yeah. Memory. Rust programs have three memory regions where data is stored. Data memory for data that is fixed in size and static. Consider the text in your program, hello world. These text bytes are only ever read from one place and therefore can be stored in this region. Compilers make a lot of optimizations with this kind of data, and they are generally considered very fast to use since locations are known and fixed. Stack memory for data that is declared as variables within a function. The location of its memory never changes for the duration of function call. Because these compilers can optimize code, so stack data is very fast to access. Makes sense. And heap memory for data that is created while the application is running. Data in this region may be added, moved, removed, resized. Because of its dynamic nature, it's generally considered slower to use, but it allows for much more creative usage of memory. When data is added to this region, we call it an allocation. When data is removed, we call it deallocation. Fair enough. Let's see. When we instantiate, I don't know, extract in our code, our program creates the associated field data side by side in memory. Extract field are accessed using dot operator. Yeah, that's good. Memory details of our example. The text inside the quotes is read only data. Therefore, it's placed in the data memory region. The function call string from creates a struct string that is placed side by side with the fields in the C creature in the stack because it's in function call, right? Creating memory on the heap for the text where it can be modified. Storing reference to that memory location on the heap and storing it in string struct. Finally, our two friends Ferris and Sarah have data structures that will always have fixed locations in our program, so they are placed on the stack. So we have our struct here, and we have function main. So we create Ferris. We tell him there is string from grab Ferris, string from Ferris name. Memory details. The text inside quotes is read-only data in data memory region. Let me see back here. Data memory. Yeah, that's the one. Okay. The function call string from creates a struct string. Display side by side with the fields in the stack. Yeah, because it's inside a function. Yeah. Okay. So this is fair enough, I guess. There we have no weapon. Weapon string from. Yeah, let's get on. Tuple like struct for location. Okay. I see. This is like named tuples. That sounds good. Pretty straightforward. Unit like structs do not have any fields at all. Okay. As mentioned in chapter 1, unit is another word for an empty tuple. This is why this kind of struct is called unit-like. This type of struct is rarely used. I see. Yeah. Nonsense, I guess. Or there is a reason, but you know, if they say you're not gonna use it often, you're never gonna use it. Enumerations allows you to create a new type that can have a value of several tagged elements using the enum keyword. Match helps ensure exhaustive handling of all possible enum values, making it a powerful tool ensuring code quality. Oh, this is what I was talking about. Like this allow that code macro or modification or whatever it's called. Yeah. So we create a C creature, species grab. So we have this species, yeah, okay. And we match the species right here. Yeah. This sounds good. Let's carry on. Oh man, how far am I? Chapter 2. Oh, that's a lot of chapters. Dang it. What's the time? Yeah, I mean, this is just intro and we can continue on the other streams. So, enumerations with data. Enum elements can also have one or more data types, allowing them to behave like union from C. I don't know union from C. Where an enum is pattern matched using match, you can bind a variable name to each data value. Memory details of enum. Enum data value will have a memory size equal to its largest element. This allows for all potential values to fit in the same space of memory. This makes sense. In addition to element data types, if any, each element also has a numeric value that represents which tag it is. In addition to element numeric value that represents which tag it is, okay. Rust enum is something also known as tagged union. Why not? It can be the combining of types to make new types. So people mean Rust has algebraic types. The combination of types to make a new type is what people mean when they say Rust has algebraic types. Enum species, enum poison type, size, weapon. What's this? Well, weapon, claw. Okay, C creature has weapon, and then when I define it, weapon claw. Okay. I wonder how I get it from. Oh, I see. It's tuple. So species crap. Match Ferry's weapon. Weapon claw. I see. This is how I get the information from the tuple. This is useful. That's great. And match size. Got it. Print line. Print line. This sounds good. Next, chapter 3, conclusion. Generic types. Oh yeah. This is gonna be juicy. Generics. I like generics. Let's go. What are generic types? Generic types allows us to partially define a structure or enum, enabling the compiler to create fully defined version at compile time. Rust generally can infer the final type by looking at our oh, I cannot pronounce that, man. But if it needs help, you can always explicitly operate, also known by the name Turbofish. He's a good friend of mine. Okay, Turbofish. Wow, why not? So we have Bank of Holdings, Turbofish. Man. Item. Yeah, this makes sense. Yeah, generic types, classic. Representing nothing. In other languages, the keyword null is used to represent an absence of value. It's great difficulty in programming languages because it creates the possibility that our program might fail when interacting with a variable field. Rust does not have null, but it's not ignorant of the importance of representing nothing. This pattern of providing a non-alternative representation for one or many alternate values is so common in Rust because of its lack of null value. Enum item, inventory string. None represents the absence of an item. Struct back of holding. I don't understand why there is none here. Darko, why is the none here? Absence of an item. This pattern. Inventory string. I mean, why would I put none there? I mean, like, what's the point? Back of holding. Next. Option. Rust has a built-in generic enum called option that allows us to represent nullable values without using null. This enum is so common, instances of the enum can be created anywhere in the enum variants. Anywhere with the enum variants, some and none. Oh, okay. Some, see. Okay. Back of holding T. Item option T. Item none. Oh, item is none. Oh, I see. Okay. I see. Sum 32. This sum is none. So this is like. Oh, alright. Yeah, makes sense. Like, if you want to know if there is an actual value, you will call it sum. If you want to know if it's none, you will call it none. It's none. Makes sense. Match sum. I see. Here we go. This looks good. Result. Oh, another one. Okay. Here we go. We talked about it, Darko, right? Result. Here we go. It's built-in generic enum called result that allows us to return a value that has the possibility of failing. This is idiomatic way in which the language does error handling. Here we go. That's important one. Oh, looks good. Result. Okay, so if I is equal to 42, I will return okay, which is 13. And match the result if it's okay. So this is like a try catch basically. Yeah, I mean, I like this because here you know what error you're gonna get. What's the type of the error? In JavaScript, it's always unknown. You never know what you're gonna get. But yeah, I believe this is even something similar in Go or these other languages, right? So, uh, failable main. Main has the capability of returning a result. Main returns no value, but it could return an error. I see. Why not? Return something went wrong. Something went wrong. Standard error. Yeah. I mean, everything fails all the time, as Werner Vogels was saying, or someone from AWS, I believe. So this makes sense. The result is so common that Rust is a powerful operator. Oh, here we go. For working with them. These two statements are equivalent. Do something that might fail. Match, do something that might fail. Well. Do something that might fail. Well, but what is inside we? Do I get this? No. I mean, this sounds good, but what happens when there is an error? What's happening? Because I mean, match. Oh, okay. Never mind. I get it. It's written right here. So if it's everything okay, it returns the result. If it's error, it returns the error. So that's why we need to have this result here, and it needs to expect string because this one is also returning string as error. Okay. Fair enough. Let's carry on. Ugly option result handling. Working with option/result can be tedious when you are just trying to write some quick code. Both option and result have a function called unwrap that can be used for getting a value in a quick and dirty manner. Unwrap will get the value inside option result. If the enum is of type none/L error, it will panic. Okay, these two pieces of code are equivalent. I see. Unwrap. So this is like in JavaScript where you're not using try catches, you just like write your code, you know, and then if there is some error path in a way, the whole app will fail. Which I mean, in some cases can be okay, but you know, most cases you might want to find a way how to handle errors. Okay. Yeah, I'm gonna have to plan the next stream, or like the next stream is gonna be about Cloudflare. Make sure to watch that because I will be exploring Cloudflare and try to do some stuff with that. But after that, maybe I could do like hands-on Rust, because today it's a lot about like going through this tour of Rust and you know, looking around. But yeah, I mean, I want to get my hands dirty and try to do something with Rust. Maybe deploy Lambda functions, because I think from Benjamin there is this serverless Rust or something like that, right? Great job with that. How to deploy Rust into AWS. And yeah, we'll see. So vectors. You mentioned it, Darko. Some of the most useful generic types are collection types. A vector is a variably sized list of items represented by the struct vec. The macro vec lets us easily create a vector rather than manually constructing one. I see. Vec has the method iter, which creates an iterator from a vector, allowing us to easily put a vector into for loop. That's good. Vec is a struct, but internally it contains reference to a fixed list of its items on the heap. That's the slow memory, right? The heap. A vector starts within a default capacity. When more items are added than it has capacity for, it reallocates its data on the heap to have a new fixed list with large capacity. Okay, so that's what I was looking for. So we create a new vec of integers. Yeah, we use turbofish. And we push the values. But look how clever Rust about determining the type automatically. Oh yeah, I mean, why not? This looks nice. Never forget about mute. That is mutable. And here we can create vec, which is, oh, it immediately creates this vector with the default values hello world, and then we create an iterator from it and print out the words. And if I do like this, string vec push string from I semicolon string vec, oh, I see, mutable. There you go. There you go. There is some Rust code right there. Chapter conclusion. What's the conclusion? Don't worry if you don't know how to use everything. Our functions are getting quite lengthy. Ownership and borrowing data. Rust is a unique paradigm for managing memory compared to other programming languages. We are going to look at the behaviors and validations of the compiler one by one, so it's not overwhelming. Okay, it's important to remember that ultimately the rules we show don't exist to make your life hard, but to help you make your code less error prone. That's what I'm telling someone when they're complaining that my TypeScript code is too complicated. It's just not trying to make your life hard, but try to make the code less error prone. Exactly. That's what I'm saying. Ownership is okay. Binding to a variable name creates memory resource that the Rust compiler will validate through its whole lifetime. Okay. The bound variable is called the resources owner. We initiate structs and bind to variables to create memory resource. Okay, who is the owner? Yeah, I mean, makes sense. Rust uses the end of scope as the place to deconstruct and deallocate resources. I see, it's dropped here. The term for the deconstruction and the allocation is called drop. Okay. Rust does not have a garbage collection. This is also called resource acquisition is initialization. Ray in C++. Okay. Dropping is hierarchical. When a struct is dropped, the struct itself is dropped first, then its children are dropped individually, and so on. By automatically freeing memory, Rust helps to ensure that there are fewer memory leaks. Memory resources can only be dropped once. Who is dropped? Ah, okay. I see. So, I mean, I would expect this to be the other way around. But, I mean, who am I to judge? Why not? Moving ownership. When an owner is passed as an argument to a function, ownership is moved. The function parameter after move, the variable in its original function can no longer be used. During the move, the stack memory of the owner's values is copied to the function called parameter stack memory. Oh, let's see. So foo do something. Foo can no longer be used. Wow, okay. Yeah, I mean, F is dropped here. Okay. Good to know. Good to know. Good to know. Ownership can be returned. Okay. Foo becomes the owner. Foo is dropped because... Wait. So if I do this and do this, Okay. Ooh. Okay. Due to, yeah, warning. Okay. Sounds good. Yeah, so if you return it back, then the ownership can get transferred back. Okay. Um so we have 7 p.m. Yeah, you know what? I will push this a bit and I will go through some more. So maybe we might do 20 or 30 minutes more. Yeah, let's see. I mean, let's get this done. Borrowing ownership with references. References allow us to borrow access to resources with the end operator. References also dropped like other resource. Oh yeah, here we go. Like this is like the not pointers, but something like pointers, right? Um who references borrow access to resource. F is dropped here. Who is dropped here? Okay. Let's do something more complex. Borrowing mutable ownership with references. We can also borrow mutable access to resources with the mute operator. Okay. Okay. So I will say I want here to be mutable who. Do something who would fail because foo cannot be moved while mutably borrowed. Oh, okay. Failure. Foo.x would fail because foo is not modifiable by mutably borrowed. Okay. Okay, so it's like only the latest borrower can do this. Can I do this? Like cannot borrow foo as mutable more than once at a time. Yeah, okay, so I can borrow only once at a time. And okay, F is dropped here because it's no longer used after this. Wait. What? This works now because all mutable references were dropped. Oh, yeah, it's foo. Okay, got it. So it's like no longer being used here. So we can get back. All right. And move ownership to function. Yeah, I mean, this makes sense. I mean, you want to know, you only want to have one place where it can be mutated at the time. So using mute references, you can set the owner's value using the asterisk operator. Here we go. Get a copy of owner's value. Oh, you can also get a copy of owned value using the value can be copied. We will discuss copyable types in later chapters. So I have my mutable foo 42. I will create a mutable, how it's called, I will like borrow the ownership here, and I will create this bar and get a copy of it. Set references owner. I'm confused now. So I get ownership here. I will set bar to the value. Okay, so okay, I'm no longer using references, but I will just go here right now, copy the value which is currently stored in F and store it in bar, and the bar is the owner of this new value. And then I will have this F, which where I'm using this asterisk, so I'm now going back to foo basically and mutating it to 13. Then F is dropped, bar is locked, foo is locked, bar is dropped, foo is dropped. I guess something like this, right? Passing around borrow data. Rust rules for references might be summarized by: Rust only allows there to be one mutable reference or multiple non-mutable references, but not both. Okay. A reference must never live longer than its owner. Yeah, this makes sense. This doesn't tend to be a problem when passing around references to functions. Okay. Memory details. The first rule of reference prevents the data races. What's a data race? A data race when reading data from data has the possibility of being out of sync due to existence of a writer to the data at the same time. Ah, okay, I see. So yeah, in order to avoid these race conditions that you're reading the data, it's changing in your hands. This way only, like, if you're mutating the data, you can read it, but not more. The second rule of references prevents the misuse of references that refer to non-existing data, called dangling pointers in C. So I will declare mutable foo, do something, and here I will pass the ownership, right? I see. So here I expect the past ownership. And I modify it. And then I drop the F. So it's released. Because all mutable references are dropped within the function do something, we can create another. Ah, okay. Got it. References of references. References can even be used on pieces of references. Oh man. Okay. Let x is a mutable reference to the x. Yeah, this way I will override the value of x here, and x is dropped because it allows us to create a non-mutable. It's dropped here. Allow do something. Okay, foo. So we expect so it should be 13, right? Yeah. Okay, next. Explicit lifetimes. Even though Rust doesn't always show in the code, the compiler understands the lifetime of every variable and will attempt to validate that the reference never exists longer than its owner. Function can be explicit by parameterizing function signature with symbols that help identify which parameters and return values share the same lifetime. The lifetime specifiers always start with okay. So do something. A who is a okay, who mute who x do something who well, the parameter foo and return value share the same lifetime. Well, okay, I mean, we'll see when we will use such feature. And multiple lifetimes. Lifetime specifiers allows us to be explicit. A and B. Foo A and foo B. And it's related to B. Return foo BX. Foo A is dropped here because only foo B's lifetime exists beyond here. Okay. And I mean, X is dropped here. Well, I don't know when I will use it, but okay. Static lifetime. Static variable in memory resource through programming. They must have their types explicitly specified. A static lifetime in a memory resource that lasts indefinitely to the end of program. Static string. String literals have a static lifetime. Unsafe. You can break some rules, but you must be explicit. We can set secret to a string literal because it's also static. Okay. If I run. So let's see. Memory. You cannot make memory guarantees. Modifying static variables is inherently dangerous because they are globally accessible and can be read from by anyone. Okay, got it. So you can do it. You should not do it. Only do it in edge cases. Lifetimes in data types. Whoa, 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 whoa. What's this? Okay. I create foo. Okay, I give it like the ownership of X. What if I do like this? Hey, it's never used. Okay. We can't have structs running around with the references pointing to nothingness. Rust validates that the containing the structure of the references. Okay. So, what's the conclusion from the chapter 5? Congrats for making... Okay, hopefully unintentional modification of Rust language aims to solve many of these common challenges in systems programming. Unintentional modification of resources, forgetting to deconstruct resources, resources accidentally being deconstructed twice, using resources after they have been deconstructed, data races caused by writing to resources while others are reading from resources, seeing clearly areas of the code where the compiler can't make guarantees. That's fair enough. So chapter 6. How many are there? Chapters 6. Oh, damn it. Yeah, I guess we are gonna finish this on the next stream. So yeah, thanks everyone for watching. I mean, today we went through the basics of Rust. Maybe hopefully this was useful for you to, you know, see how Rust works, maybe compare it to TypeScript. And in the next stream you can look forward for me exploring Cloudflare. It's going to be very interesting to see all the services they have. Maybe we will deploy the apps through the Wrangler, I think it's called, the tool for deploying the workers, and explore their offering, because, you know, many people still think Cloudflare is just CDN company, which it probably mostly is, but they are pushing hard on becoming an actual cloud provider, I would say. They did a couple of acquisitions recently, like they acquired Baselime. Kudos to Boris and his team, Boris, Thomas, and others. Very good job on that. I mean, that's what Cloudflare was missing, some observability, and it's very important nowadays. So here we go. Baseline team goes for building observability in Cloudflare. That's great news. And yeah, and then after that, probably we'll get back to Rust and finish it up. I think it's going to be interesting one. So yeah, thanks everyone for watching. Thanks for coming, Benjamin and Darko. And yeah, take care. Bye.